What happens to a limiter when we use the constant voltage drop model? So the constant drop model, remember, means we have, we replace a silicon diode with a 0.7 volt kind of voltage source, one that can't supply a current. It means that when the diode is off, it's an open. Oops. And when the diode's on, it's no longer a short, it's a 0.7 volts for silicon. So if the diode is facing this way, then it becomes a voltage source with 0.7 volts on it. But like I say, there's no current supplied by that. It's just simply a 0.7 volt appearing in place of the diode. Well, for this limiter here, when we, if you do it with the, for this one with the ideal model, we get a V out, that's interesting, versus V in, a transfer characteristic with the ideal model. And we figure out what's going on the same way, whether it's the constant drop model or the ideal. With the ideal model, for Vn is minus infinity. For minus infinity, the diode must be on. It's a short, and that means that we just see this. If we replace the diode with a, if we replace this diode with a short, then we just see minus 5 volts on the output, and we have a constant minus 5 for the output. Now, if we have, let's make that a little flatter, certainly not a whole lot flatter. If we have plus infinity, I don't know why it sometimes does that. What is going on? Oh, it's because it thinks I'm drawing a line. So plus infinity equals Vn. The diode is off. When it's off, we replace it with an open circuit, and we simply have this line here. That's the ideal model. So what happens with the constant drop model? Well, we have those same two situations with the constant voltage drop model. With the constant drop model, when Vn is equal to minus infinity, we have an open circuit, and V out is equal to Vn. V out and Vn. Sorry, I didn't say that right. When we have it as an open, then we see this minus 5 volts, but now we see something more. We see we see, so Vn is minus infinity. It's not an open, it's a 5 volt battery. The diode is a 0.7 volt battery. So if I replace that circuit with the 0.7 volt source, we have to make sure that we get it in the same direction as the diode. So it's like that. And then we still have minus 5 volts here. We have plus 0.7 here. And so we go from minus 5 and And we drop a further 0.7 volts. So then we would have my V out is equal to minus 5.7, because we're dropping a further 0.7 volts through this battery here, right? When the diode is, or when Vn is equal to, or sorry, let's draw that in. For minus infinity, we have minus 5.7 volts. When Vn is plus infinity, it's open again. And we have this circuit like that. So plus infinity means we're out here. And we get a transfer characteristic that looks like that. Should be a 45-degree line. Erase some of those if I can be precise. No, I can't. Get this 45-degree line, and the only difference with the constant drop model is that we have added this 0.7 volt battery, but it's not a current source, and it you just the critical thing is to get the direction of the diode right, and the resulting change in voltage. If it helps you to draw it a little more fully, to draw it like this, then we have minus 5 volts, so that's going this way too. So we got minus plus 5.0 plus minus 0.7. And so you can see it clearly there that we've dropped down to minus 5.7 in that case. So be careful about those directions, and it should work out for you. If the diode was reversed, if it was pointing the other way, then we would have gone to minus 4.3 volts just by the direction of that battery. So be careful about the direction of the diode, and adding that constant drop shouldn't cause you any problem.